Over the next few videos, we're going to be taking a closer look at the electric field that arises from a finite line charge along the z-axis. So what we want to do is we want to find the field at some arbitrary point due to this line charge, which we're going to say has uniform charge density, rho L, between 2 points A and B on the z-axis. So what we have is something that looks like this, where our blue curve or our blue line there represents our line charge. And so what we're saying is we want to find our electric field at some arbitrary point x, y, z. And so just as a note on notation, typically if we're talking about a field point or an observation point, as I've drawn up here, we just have unprimed variables, in this case x, y, z. And if we're talking about a source point, so remember we're essentially breaking these up into a lot of point charges when we evaluate the integral, we're going to use prime notation for that. So we'll say those are at point x prime, y prime, z prime. So what we want to do is we want to be able to use our general form of the integral equation from the previous video. And remember, we need to find three things for this particular problem. We need to figure out what our r is, we need to figure out what our unit vector in the r direction is, and we need to figure out what our dl is. Okay, so we can start, we need to consider a dl segment of our line. So let's say if we sort of zoom in here, let's say we can consider some differential length. So this is some dl. And so let's say this point dl, of course it's going to have 0x and 0y. So let's say this is at point 0, 0, and again this is our source point, so we're going to call that z prime. Okay, so now we can talk about a little bit our z, or sorry, not our z, we can talk about our differential length, and that's going to be, as we see, only in the z direction. In order to talk about our r vector, we need to draw a connection point here, and our r vector is going to be like this. So from that, we can find the magnitude of our r, and ultimately our unit vector in the r direction as well. So let's start by saying that our dl is going to be just in the dz direction. So we can say dl is equal to dz. And so this is going to be dz prime because, again, we're talking about the source point, and this is only changing in our z direction. Okay. The next thing that we can do is we can figure out this r vector, which is the distance between our differential length and our arbitrary point x, y, z. So going back to our basic vector algebra, we can say that that vector r is just going to be x, y, z minus 0, 0, z prime. And so what we get then is we get x in our x direction plus y in our y direction, plus the quantity z minus z prime in our z direction. And so what I can do is I can convert this to polar form or convert it to cylindrical coordinates using our transforms from our previous unit. So convert to polar form slash cylindrical coordinates using our transforms from chapter 2. And so if we do that, what we get is that our r vector is equal to rho in our rho direction plus z minus z prime in our z direction. And so let's come back up to our figure and update this a little bit. So our rho is going to be defined as the distance from our z-axis. So let me put a dotted line indicating that distance here. So something that looks like this. And so let me actually, let's see if I can get that lined up a little bit better, and it might not let me. All right, let's see. All right, there we go. And so this would be our rho distance here. And so note, in this particular case, our rho definition is lining up with how we defined rho in cylindrical coordinates in the previous chapter, or not the previous chapter, but in a previous unit. But what we want to keep in mind, and I'll come back to talk about this in a later video, is that this isn't necessarily going to be the case. For instance, if we moved this charge distribution to our y-axis, rho would be the perpendicular distance from the y-axis. In this case, it just happens to align with our previous definition because our line charge is along the z-axis. Okay, so we've simplified this a little bit by putting it into our polar form. So now what we want to do is ultimately, remember, we want to find our unit vector divided by r squared. So let's start by finding the magnitude of r squared. So we can say the magnitude of r squared is just equal to r squared, which we had in our general equation. So we can find that is just rho squared plus the quantity of z minus z1 squared. And then ultimately the term in our equation though was the unit vector divided by that. And so really we know that's just r divided by r cubed. And so what we can say then is that that quantity is equal to, so our r we said is rho in our rho direction plus z minus z prime in our z direction. And then we're taking that rho squared and raising it, or we're taking our r rather and raising it to the 3/2 power. So we have rho squared plus the quantity z minus z1 squared, and then raising that to the 3/2 power. Okay, so now we know our u of r over r squared. We had previously found up here our dl, so now we're ready to plug into our general equation. And so this is our general equation from the previous video where we were talking about line charge distributions. So our electric field then is equal to the integral along the line of, and so just to copy that equation here real quick, so we had rho L dl divided by 4 pi epsilon naught r squared unit vector in the r direction. And so we can pull out some constants here because we said we have a uniform charge density rho sub L. So this is a constant value for all rho, all z. This can come out in front of the integral, as well as our 4 pi over epsilon. Those are just constants. So we have rho L divided by 4 pi epsilon naught integral of over the line. And then we have this term right here in the integrand. So we have rho in our rho direction plus z minus z prime in our z direction divided by, so we have rho squared plus the quantity of z minus z1 squared to the 3/2 power, and then we multiply by our dl, which we said was dz primed. And so to be consistent with the notes, I'm going to call this equation 1. And so what we're going to do in the next video is we're going to come back and we're going to look at how to evaluate this integral.